All right, welcome ladies and gentlemen. This is the second of the flip lessons on using enthalpy. And this method that we're going to be focused on today is something called Hess's Law. But before we can get into Hess's Law, I have to define a term that we are now likely to see from here on out in our discussion of thermochemistry. And it is the very slight distinction between enthalpy and something called standard enthalpy. So you have enthalpy, which is your heat that's involved in a chemical reaction that we've been talking about so far. Standard enthalpy is enthalpy that was determined under a set of essentially predetermined conditions, what we call standard conditions. Now, standard conditions when it comes to issues of thermodynamics, which includes thermochemistry, are actually not the same as STP. STP is 0 Celsius and 1 atmosphere of pressure. Well, the 1 atmosphere of pressure is the same, but the temperature is not. So our standard conditions in terms of thermodynamics are 25 degrees Celsius, 1 atmosphere. And if we are dealing with solutions, 1 molar concentrations for all solutions. Now, I mention this because you're likely to see this term, this symbol pop up, delta H, and then we have something that looks like a little degree sign. It's not a degree, and the way we read that is not. So I would read that as delta H naught. So it's not N-O-T, it's not something you tie in your shoelaces, it's not N-A-U-G-H-T. And it's simply a signifier that when you see it, that enthalpy was determined under these standard conditions, 25 degrees Celsius, 1 atmosphere pressure. You will treat that delta H value exactly the same way as you've been treating delta H values thus far. So nothing changes in terms of what it really means or how you use it or what math you do. It simply means that we had a certain temperature and a certain pressure and certain molarities when that value was determined. So Hess's law. Hess's law is a means of determining enthalpy because, again, enthalpy is a state function. It is independent of path. That means that we have lots of ways of getting enthalpy. Just like if you were to pick 2 locations on a map, you could figure out many different routes to go from point A to point B that would all fundamentally get you from point A to point B, but they'd all be different paths. Hess's law is one such path to determine the enthalpy of a chemical reaction. The idea behind Hess's law is, well, if we are allowed to take different routes to get to the enthalpy of an equation, then why don't we consider reactions that kind of look like the equation we want but aren't exactly the equation we want, manipulate them in some way, and then add them together to get the reaction that we want, and then ultimately the delta H value that we want. Hess's law is all about adding equations together to get what you want. And when you add reactions together, you're actually going to also add the enthalpies together for those reactions. You'll see what I mean. There are some rules for Hess's law, and they're essentially the exact same rules that we've mentioned thus far for enthalpy, meaning, number 1, if you have to reverse a reaction, you have to flip the sign on the enthalpy for that reaction, meaning a reaction that is exothermic in one direction, in the forward direction, will be endothermic, have a positive delta H value instead of a negative delta H value in the opposite direction. This is something that becomes crucial in Hess's law. Number 2, if your reaction coefficients are altered in some way, the delta H value must be altered in the same way, meaning you take all of your coefficients of your reaction and you multiply all of them by 2, you're doubling your reaction. You must also double your delta H value because delta H depends on amount. Delta H is very much tied to the quantity of stuff that you are reacting. Remember, delta H is directly linked to the molar ratios as written. So if you make those molar ratios twice as big, you're going to make your delta H value twice as big. What this really comes down to is whatever you do to your reactions, if you flip them, if you multiply them by something, if you divide them by something, if you add them together, you have to do the exact same thing to your delta H values. However you manipulate your reactions, manipulate your delta H value in the exact same way. So what does a Hess's law problem look like? This is what a Hess's law problem looks like. The reaction will give you, the problem will give you a reaction right here. A plus B goes to E plus F. We're starting really simply. And then it gives you all these other reactions that are somewhat related to the target reaction, but they're not quite the same thing as the target reaction. And they say, hey, what is delta H for this target reaction? What is delta H for A plus B goes to E plus F? This is a Hess's Law problem. And I actually kind of like Hess's Law problems, again, because I'm nerdy and I'm proud of that. But Hess's Law problems to me, they're like little puzzles. That's really what they are. They're like little puzzles. They're saying, hey, how can we get this target equation right here from these other three equations that look kind of like it but aren't exactly it? So the way that you approach this puzzle, because it is one, is by simply taking the three reactions that you've been given that aren't quite the target reaction and thinking about what they give you that you need in the target equation. So what do I mean by that? Well, if I look at this first reaction, A plus B goes to C plus D, and then I look back at my target equation. I say, what do they have in common? What's in this first one that I want in my target? And I see immediately the A plus B, right? A plus B. Now I think, okay, so that's what's going to give me my A plus B out of these three reactions. And then you have to ask a couple of questions. Number one, are the A and the B here in the same spot of the on the same side of the arrow as they are in the target equation? Meaning, are they reactants or are they products? Well, in the reaction that we're given, the A and B are the reactants. In the target reaction that we want, A and B are reactants. That's good. That means that we don't have to manipulate A plus B goes to C plus D in any way. Then you have to ask, is it the right quantity of A and B? In our target reaction, we only want one A and one B. Well, in the reaction that we've been given, we only have one A and one B. So we have the right quantities of A and B, and we have them on the correct side of the equation. So I'm going to write next to this a keep, meaning I don't need to manipulate this equation at all. It's fine as is. It gives me something that I need on the side of the arrow that it needs to be on, and in the number of things that I need. Next, we're going to look at the second equation. The C goes to E. And I'm looking for things that are in C goes to E that are also in my target equation, and I immediately notice E, right? E. So that second equation gives me E. Now, then I think, okay, what side of the arrow is E on here? Well, here it's on the right side of the arrow. In the target equation, it is also on the right side of the arrow. So I have E in the correct location. Then, do I have the correct amount of E? Well, I look at this, and there's only one E in that reaction. Looking here, there's only one E in that reaction. Okay, great. It's the correct number and it's the correct location. So I'm going to write a keep next to that. And then I'm going to look at the last one, F goes to D. Again, I'm looking for things that are in F goes to D that are also in my balanced equation. And I notice in the reaction that I want that we have an F. We have an F. Well, I need an F. First thing that I ask, is the F on the correct side of the arrow? Ooh, no, it's not, because here F is a reactant versus here F is a product. So that immediately means that I'm going to have to flip this equation around. I'm going to have to write it backwards. Instead of F goes to D, I'm going to have to write it as D goes to F. Then I'm also thinking quantity. There's only one F in this reaction. There's only one F in my overall reaction, so I don't need to multiply that by anything, but I will need to flip the reaction around. That's Hess's law. Once you've figured out how you need to manipulate all these reactions, then I strongly recommend that you actually rewrite all of the equations. Now, the flipping, which we have to do in that third one, means for the delta H value right here, you're going to have to flip the sign. Because if you reverse F goes to D, which is negative 25 joules, and you write instead D goes to F, now that delta H value would be positive 25 joules. So on the next slide, and this is simply saying that then, what I have here is the result of that. So I've rewritten the equations. So I still have the A plus B goes to C plus D, because I kept that. I didn't change that at all. I have the C goes to E, I kept that, I didn't change that at all. But I have, in fact, flipped the F goes to D, and now it's D goes to F. So you'll notice we have a positive 25 joules. And now, add them together. When you add these three together, they should give you the target reaction, the one that we want. The way you add reactions together, I like to, first of all, notice how I've lined up the arrows? Keep that arrow in the exact same spot. Everything on the left-hand side of the arrow stays on the left-hand side of the arrow. So if it's originally written on the left, you keep it on the left of the arrow in your overall. Everything that's on the right-hand side of the arrow stays on the right-hand side of the arrow. You're not going to take something that's a reactant in one reaction and then make it a product in your final equation. But if there's anything that's identical on both sides, kind of like a spectator ion, actually very much like a spectator ion, you're going to remove it and it won't be in the overall. So we see here that in this one, in the second reaction, we have C on the left, and in the first one we have C on the right. That won't be in our final equation. Likewise, we have D on the left, and then D on the right, so that won't be in our final equation. But everything else is different, so I'm going to add them together. So I'm going to keep on the left-hand side of the arrow the A plus B, and then I'm going to keep on the right-hand side of the arrow the E plus the F, and that's going to give me my overall target equation, which is good because it tells me that I manipulated these reactions in the correct way. You need to be able to manipulate them so that they give you the overall target, which you did. My smartboard is having a moment right now. All right, so we have E plus F, which is what we want. Now, we wanted the delta H value for this reaction. A plus B goes to E plus F. Well, what did we do to the reactions? We added them together. Whatever you do to your reactions, you must also do to your delta H values. So you are now going to add your three delta H values together, keeping in mind, again, that you flipped the sign on that third one, but just simply sum them up, and you will have the enthalpy value for this equation. So 55 plus a negative 32 plus 25 joules, we have an enthalpy value of positive 48 joules for that reaction. That's Hess's law. That's what it is. It's this idea of adding equations together to get the reaction that you want. And I just have two more examples of that we're going to see in this video. And then when I see you next, you will be practicing this for me. So calculate delta H for this reaction. Now we have a real equation. 2N2 gas plus 6H2O gas yields 3O2 gas plus 4NH3 gas. And then we were given reactions that are related but aren't quite the reaction that we want. So it's a puzzle. We got to figure it out. How do we have to manipulate these suckers to get what we want? So first of all, I'm going to look at equation 1. I'm going to call it equation 1 and equation 2. Equation 1 has NH3 gas goes to 1/2 N2 plus 3/2 H2. Okay, look for things that are in this reaction that you want in your overall. And the first thing, there are actually two of them in here. The first thing that I noticed, though, is the NH3. Because in the target, we have NH3. So it gives us the ammonia. But it doesn't give us the ammonia in the right place, because the ammonia in reaction 1 is on the left side of the arrow, but we want the ammonia on the right side of the arrow. So immediately that tells me that I'm going to have to flip this reaction around. I'm going to have to reverse it, which means I'm going to have to negate the sign on delta H. Then, looking at quantities, in reaction 1 right here, there's only one ammonia. There's only one NH3. But in the reaction that I want, there are 4 ammonias. That means that I'm going to have to multiply this entire equation by 4. Because I need to have 4 times as much ammonia. I only have 1, but I need 4. Which means that I will also have to multiply the delta H value for that reaction by 4. So I need to flip this sucker around and multiply every coefficient by 4. So I'm actually going to do that right now. So flipping this, my reactants are going to be my products and then vice versa. Flipping and multiplying times 4. So I'm going to wind up having a 4 NH3. I have to multiply the 4 times the 1/2 for the N2, and I have to multiply the 4 times the 3/2 for the H2. So I'm going to wind up with 2 N2 gas plus 6 H2 gas yields 4 NH3 gas. I'm also going to figure out that delta H value right now. So I'm going to flip the sign. So instead of being positive, now it's going to be negative, and then I'm going to multiply it by 4. And from that, I get negative 184. So negative 184 kilojoules. That's the delta H for this manipulation that I've done. Okay, now I'm going to have a look at reaction number 2. So again, I'm going to look at reaction 2, and then I'm going to look at the equation that I've been given, which is up here. I'm going to figure out, what's in reaction 2 that I want and need, and where is it, and how many of them are there. So I notice that we have O2 in reaction 2, and we have O2 in the target reaction. We also have water. That's you can do the exact same things with the water as well. But the oxygen is not in the right place. In reaction 2, the oxygen is on the left-hand side of the arrow. In the target equation, the oxygen is on the right-hand side of the arrow, which tells me that I'm going to have to flip this reaction. So instead of being negative 484, it's going to be positive 484. Then I don't have the right quantity of oxygen. I only have 1 mole of oxygen here, but I need 3 moles. So, like with the other one, I need to multiply this entire equation by 3. So instead of 2 H2 gas, I'm going to have 6 H2 gas. I'm going to have 3 O2. I'm going to have 6 H2O. So I need to flip it and multiply it by 3. So I'm going to rewrite the equation. See, the rewriting becomes very helpful. Because then you can keep your manipulations very, very clear. So I'm going to flip this thing and multiply it by 3. So I'm going to wind up with 6 H2O gas yields 6 H2 gas plus 3 O2 gas. And then the delta H, it's going to be positive 484, flip the sign, times 3. And when you do that, you get positive 1,452 kilojoules. If we have manipulated these correctly, when we add the reactions together, we're going to get the reaction that we want, the 2N2 plus 6H2O. So I'm going to add these together and see if I've manipulated them correctly, crossing out anything that is the same on both sides of the arrow. Well, I immediately see that we've got 6H2 here and 6H2 here, so that goes away. There is nothing else, though, that is the same on both sides, so I'm going to keep everything on the left. So 2N2 gas plus 6H2O gas yields, keep everything on the right-hand side of the arrow, 4NH3 gas plus 3O2 gas. I added which is the target reaction, so I know I've done the manipulations right. Whatever you do to the reactions, you do to your delta H's. You added the reactions together, so you're going to add your delta H's together. These guys, right? These are the ones that we're going to add. When you add that together, you get a delta H value for this reaction of positive 1,268 kilojoules per mole of reaction. That's Hess's law. It's a puzzle. It's fun. You're trying to figure it out, crack the code. How can you manipulate what you've been given to get the reaction that you want? And then our last example. Calculate delta H naught. Oh, here's the delta H naught. We're going to treat it the exact same way. Does not matter. Doesn't really make any impact on the concept of Hess's law. Delta H naught for the following reaction, NO gas plus O gas goes to NO2 gas, given the following information. So again, taking it one by one and figuring out what are we going to do to this. So I'm going to label these just reaction 1, 2, and 3. And I look at reaction number 1, and I'm looking for things that I want that are also in the balanced equation that I want. And I notice, for example, we have NO on the left, and there's one of them, and we have NO on the left, and there's one of them. And then we have NO2 on the right, and there's one of them, and there's NO2 on the right, and there's one of them. So I have things that I want on the correct side of the arrow in the correct amount that I want. I'm going to keep this reaction. I'm not going to manipulate it. I'm going to keep it as is. Then I'm going to have a look at the second reaction. Well, the second reaction has O3 and O2, neither of which are in the overall. Okay. I'm going to come back to that then, because that one is not obvious, at least not at this point, with what I have to do with it. So, okay, you get one that maybe you don't really know what it's there for. Keep going, keep going. And then we have the third reaction. O2 gas goes to 2O gas. So this one, when I look at the overall reaction, and this one gives me the O, which is in the overall, but I don't have the right amount of O, and it's not on the right side of the correct side of the arrow. I only want one O, and this has 2, so I know I'm going to have to divide everything by 2. And I want it on the left instead of the right, so I'm going to have to flip it. So I'm going to rewrite the two reactions that I know what I'm doing with right now. So I know I'm going to have NO plus O3 yields NO2 plus O2, so I'm not changing that first reaction at all. So the delta H is minus 198.9 kilojoules. And then I'm going to do my manipulations to the third reaction. So I'm going to flip it and divide everything by 2. So I'm going to wind up with O yields 1/2 O2. So this delta H, again, flip and divide by 2. So I'm going to have negative 495 divided by 2, which is minus 247.5 kilojoules. And now let's go back and have a look at that second reaction. Now I'm going to start to look at what I've done so far and figure out, what I need to do with that second reaction. Well, I notice, for example, that I have this O3 that's in my first reaction that is not in the overall. It's not here, but it's also not canceling with anything. The purpose of this second reaction is to cancel stuff. It's to help you get rid of things that are in reactions 1 and 3 that you don't need. And if I know I need to cancel the O3, then I need the O3 on the right-hand side. So I'm going to have to flip this to get the O3 on the right-hand side. So if I flip that reaction, I'm just going to rewrite that flipped around here. Then my delta H value is going to be positive 142.3. Sometimes you need a reaction to cancel stuff that you, not necessarily give you things, but cancel out stuff that you know you don't need. Now we can add the reactions together. Keep everything on the left, keep everything on the right, All right, anything that cancels out, again, here's that O3. The O3 is going to go away. It's on both sides of the arrow. Also canceling out. Notice that we have O2 on the left here, and then we have O2 on the right here and here. So total O2 on the left is 3/2. Total O2 on the right is 1/2 plus 1. Guess what? 1/2 plus 1? That's 3/2. I have a total of 3/2 oxygen on O2 on the left-hand side of the arrow and a total of 3/2 oxygen on the right-hand side of the arrow. If the numbers were not equal, if they did not add, you would have a net sum of oxygen on one side of the arrow, and it would be in your overall equation, which we see later. So when we add these together, we do indeed get NO plus O yields NO2. Add the delta H values together, the minus 198.9, the minus 247.5, and the positive 142.3. When you add them together, you get a delta H naught, and this will be delta H naught because these are all standard enthalpies, is equal to minus 304.1 kilojoules. Hess's law. It's a puzzle. What kind of fun. If you know you've done it correctly, if you add your manipulations together and you get the target reaction, there is no guessing. And then you simply make sure you've done the exact same thing to your delta H values.